Hello friends. So in this video, I will try to simplify Zernike polynomials in a way that makes sense to all of us who are associated with eye care, associated with ophthalmology. So we all understand that with multifocal IOLs gaining popularity, the concept of higher order aberrations have also found increasing importance in ophthalmology. So it is very important basically to understand Zernike polynomials because most topography machines, most aberrometers throw some information on patients' higher order aberrations profile, and in a way sometimes which may be confusing to us. We see some of those printouts from the topography machines, aberrometers, but we are not able to, sometimes we fail to understand what those numbers means in those printouts on Zernike polynomials from the aberrometers. So before I go ahead, friends, let me tell you that for those of you who are more comfortable in reading rather than listening, you may log on to my site quickguide.org for a write-up on this subject. So friends, recently I was forwarded this printout from one of the company's topography machine, and the person who actually forwarded this to me was confused how to interpret this data. Well, to interpret this data, we need to have an understanding of the Zernike polynomials, and we will try to interpret in a way that makes sense to us, in a way that makes sense to ophthalmology, to eye care. So friends, when you see here the Zernike polynomials, it has some strange looking numbers assigned to each circles, and the circles are equally confusing with some strange colors in it, right? So what does it mean? And when I opened the physics book, this is something that it threw out to me, right? The numerator and the denominator associated with the function z. It says that the definition of the numerator would stand for a continuous function that repeats itself every 2 pi radians, while the n would stand for a radial function that is proportional to blah 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 blah, again, which doesn't make any sense to us. So let's see how we can make meaningful sense to it so that it actually makes sense to us in ophthalmology. So friends, to help us interpret this in a way that it is meaningful to us, remember the numerator, or what is denoted as M, is basically the number of meridians of the cornea that is affected. If we are talking of corneal aberrations here, and to keep it simple, let's only talk of corneal aberrations. So the M is basically the numerator, and the numerator here is the number of principal meridians of the cornea that is affected by that aberration. So if you talk of, say, astigmatism, regular astigmatism, how many meridians are affected? There are two principal meridians that are affected, right? The principal meridian are the stick meridians and the flat meridians, right? So how many meridians? Two meridians. So when it comes to M, the value of M with astigmatism will be 2. That is, the numerator will be 2 and the denominator will also be 2, and that I will explain in the next slide, because these are all orders starting from the blue circle that you see. It starts with the order 0, then goes to order 1, order 2, order 3, order 4, order 5, right? So it goes like this. So the denominator, which is the n, is which order we are talking of. First 0 order, first order, second order. So this denominator is basically, when we are talking of astigmatism, is 2 because it is on the second order. It is on the 0, 1 and 2. So this is the second order, right? So that is why it is denoted by Z2 by 2, where the numerator M is the number of meridians of the cornea that is affected. And in astigmatism, we know we have principal meridians, are the steep meridian and the flat meridian, so two meridians. And the denominator is the order, right? And we know this line is the second order, right? 0, 1, and 2. So this line is the second order. So Z 2 by 2. Well, one important explanation I should also give over here is the aberrations could be vertical, the aberrations could be horizontal. Starting from N1 to N5, N6, whatever aberrations you're talking of, they can be vertical, they can be horizontal. So anything to the left here is the vertical aberration. Anything with the horizontal here to the right here is the horizontal aberration, which is denoted as plus. So if you look over here in these boxes, anything to the right are all aberrations which are horizontal, and therefore they have a positive value on the numerator. If you look at the left, all aberrations are vertical. So you have, for example, in astigmatism, you have vertical astigmatism, right? We have with the rule astigmatism, which is vertical. You have also against the rule astigmatism, which is horizontal, right? So any astigmatism, which is any aberration which is vertical, is denoted by minus on the numerator. Any aberration that is horizontal is denoted by a plus sign on the numerator. An exception is the M0, that is the numerator which is 0. So for example, if you see the piston over here, this first order aberration is the piston. It has neither a minus nor a plus because it falls in the middle. Again, the defocus, myopia or hyperopia here, the second order aberration over here, this is the defocus. It falls in the middle and it has neither minus nor plus values, right? It is on the middle. Then again, the spherical aberration. As we go on in the slides, you will learn to decipher these aberrations. So now we will try to understand these aberrations, what these aberrations are, right? In the first two orders here, N0 and N1, so we are now talking of the orders over here, we are talking about the denominators. The first and the second, they are all constant aberrations, right? This aberration can be equated with the piston. This aberration, which is on the first order, can be equated with the piston of an engine, right? When the piston motion is vertically moving up and down. So as the piston movement is vertically upwards and it comes closer to our eyes, right? And then it goes below and it goes away from our eyes, right? The object looks, when it comes towards us, the piston, it looks bigger, right? The more the piston moves away downward and away from our eyes, the object becomes smaller, right? So in ophthalmology, this is not a true aberration. It is only a perception. It is only an image variation because of the position, right? So since only the size of the object is varied, we call it as a quantitative variation and not a qualitative variation. So that is why this is not actually a true aberration. Ophthalmologists are not concerned about this aberration because it does not have any detrimental effect on the eyes, right, of the patient. It is only a perception. So this aberration, therefore, is not important clinically. So you will also notice that when the sun and the moon are together, visible in the pale sky, both of them seem to be of equal size, right? In the pale sky, when you see sometimes when the sun and moon are together towards the evening, sometimes you feel that both their sizes are equal, right? However, we also know that the sun is a few hundred times bigger than the moon, but we see it of the same size because the moon is also, closer to us. So now let us try to understand the Zernike polynomial attached to this aberration as seen over here, right, in this picture. which is Z numerator 0 and the denominator 0. Denominator 0 because n is 0. It's the zero order aberration. It starts with 0. And the numerator is also 0 because none of the principal meridians are affected, right? It's only a perception. We are not concerned about this aberration. So friends, next comes the N1 or the first order aberrations here. And I think I said before that the first two orders, that is the N0 and N1, are not a concern for ophthalmologists because they do not hardly affect or create any problem for the patients because it's just a perception. Because if you look in N1, this is basically the horizontal and the vertical tilt, and that tilt happens because of our perception of how we are seeing the object. For example, in this picture you can see, we can all understand that these columns are actually vertical, but the way we see it from a distance, it feels like it is a little tilted, right? Sometimes if you see a square from a certain angle, it might look like a rhomboid, but it's only a matter of perception. So we are not much worried about N0 and N1 because they're just perceptions and they actually are not detrimental to our vision. If we change our position, we will see things perfectly, right? Or if the object changes position, we are going to see it the way it is, it actually is. So coming to this N1, how do we denote it? N1 is denoted as Z minus 1, 1. So why do we say minus 1? Because it is vertical to the left side. The tilt is vertical, so we denote it by minus sign. Well, why is the numerator 1? Because the tilt is affecting only one meridian over here, right? You can see the one meridian is being affected over here. You can see it with the red color over here. And the denominator is easy to understand why it is 1, because it is on the n order. Well, the next order of aberrations, now we come into this column, that is N2, right? And here we are talking about defocus aberrations. That is, we are still on lower order aberrations, right? Up to N2 is the lower order aberrations. Here it is depicted by Z 2 by 2, right? Why? Minus because it is on the vertical side. Why is the numerator 2? Because this is astigmatism. This is the vertical astigmatism, and here is the horizontal astigmatism, right? We know that horizontal, anything that is on the right side, that is the horizontal, is plus. Anything which is on the vertical side, which is on the left side, is minus. So therefore the numerator is being assigned minus sign. Here it is positive sign. Why is the numerator 2, the value 2? That is because two principal meridians are affected in both vertical and in both with the rule and against the rule astigmatisms, right? The steep meridian and the flat meridian. Why is the denominator 2? Because it is on the second order aberration, right? These are all lower order aberrations. If you come to the middle, right, this is myopia or hyperopia. In myopia or hyperopia, how many meridians are affected? Remember, we are talking of the value of the numerator or the m. So how many meridians are affected in myopia or hyperopia? All the meridians are equally affected. So we give a value of 0 over here, because there is not one particular meridian which is affected more than the other. So therefore, since all meridians are affected in an equal way, homogeneous, therefore m is 0, neither positive nor negative, and then the denominator is 2, because you can well understand this is in the second order of aberrations. Till here we are talking of the lower order aberrations. These are the aberrations where 80% of the patient's vision is affected because of the lower order aberrations. However, the rest 20 to 10% of the vision is affected because of higher order aberrations, and we talk of higher order aberrations from N3 or the third order. So friends, there are infinite number of aberrations, right? They're like a kaleidoscope. There are n number of aberrations. But in ophthalmology, what we are concerned is up to third or fourth order of aberrations, right? So that is what is more important to us. So if we start from the third order, this is basically where the higher order aberration starts. You can well understand why the denominator is assigned a value of 3, because this is higher order aberration starts from a third order aberration, right? This line n is equal to 3. Starting here is what we have, the trefoil. So this is the vertical trefoil, and therefore it is assigned minus. Why 3? Because trefoil is always affects 3 meridians, right? Like the bilipatra. We will talk about in the next slide about how it looks like. So the trefoil is like a Mercedes-Benz symbol. It affects 3 meridians, so minus 3 by 3, the denominator is 3. Then we come to coma, the vertical coma, and vertical coma is assigned a value of 1 because only one meridian is affected, right? Tilted. Coma comes because of off-axis aberrations. So one meridian is tilted in coma, and therefore it is assigned a numerator value of 1, right? Where it is vertical coma, therefore it is also assigned minus, negative value. Then again comes horizontal coma, right? And this is opposite to the vertical coma. It has been assigned a positive value, but only one meridian is affected, and therefore one principal meridian is affected. Therefore, you get a numerator value of 1. And then again you come to horizontal trefoil, and therefore it is positive. Again, in trefoil, like in vertical trefoil, horizontal trefoil involves 3 meridians, and therefore it has been assigned, the numerator has been assigned 3, right? So say 3 by 3. So N3 is basically the order 3. The higher order aberration starts from here, starts with the vertical trefoil, then the vertical coma, then the horizontal coma, and then the horizontal trefoil. So this picture actually, you will have an idea about what a trefoil looks like. What if a patient has trefoil aberration? How does he see this? See a point source of light, and it seems like he or she sees like a Mercedes-Benz symbol, right? It's spread out in 3 directions. Those of you who are Hindus, you can immediately, identify this with the something like bilipatra, like what we offer to the Lord Shiva. Or in Gothic architecture also, you can see this architecture. You have the 3 foils, the 3 leaves over here. So we talked about trefoil. We can also speak about coma in this aberration. So these are the 2 coma aberrations, the vertical aberration, vertical coma, and the horizontal coma. Remember, of all the aberrations, coma is an off-axis aberration, meaning that if the rays of light were coming on axis and you do not have any lens tilt, there will be no coma at all. But if there is a lens tilt, or if there is an off-axis rays of light that comes to our eye, we may be having coma aberrations. And the word coma comes from the word comet. What does comet mean? I mean, the celestial body comet is basically you have a head and you have a tail, and so from there you get the word coma, right? And if you also think of the English language, the sign that we use, Coma, also has a head and a tail, right? So coma appears like that. So patients suffering from coma will see things which has a head, and then which will have also a tail, right? Something a blur like this. So friends, beyond the third order of aberration, what is important is the spherical aberration, and this is basically the spherical aberration, right? So the spherical aberration is basically a fourth order aberration, and by far the most visually significant of all the aberrations. They say the spherical aberration, the coma, and the trefoil are the three aberrations which affect our vision the most, and the spherical aberration is therefore very, very important, right? The spherical aberration of the fourth order, right? It's a fourth order aberration, and hence therefore you will see that this denominator is Z4, right? Because it's fourth order aberration. But the numerator is 0 because if a person is suffering from spherical aberration, has a large amount of spherical aberration, then all the meridians are equally affected. So so how it is denoted is Zm by n is Z, m is 0 and n is 4 because it's a fourth order aberration. If you're wondering what is spherical aberration, then spherical aberration is that the rays of light that goes through the center of the lens falls on one spot, but the rays of light that goes through the periphery are over refracted if it goes through the cornea. If we are talking in terms of corneal aberration, the peripheral rays of light actually are over refracted for most patients, right? So therefore, you have now not all the rays of light falling at the same point, and this could lead to, a drop in contrast sensitivity, a drop in image quality for the patient. So, friends, that was basically a simple interpretation of Zernike polynomials. If you want to read about it more, you can visit my blog, which is quickguide.org. Thank you very much for your patient listening. Thank you.